Hi, I am Brandy Heflin, and I'm a personalized physics instructor. I help high school and college students feel confident and successful in learning physics. I have for you today a really fun and interesting problem whose solution I wanted to share because in 22 years as a student, a teacher, and a tutor of physics, I had never come across a problem like this until one of my students brought it to me in session. The overall theme of the problem I want to share with you today is on the magnetic force between current carrying wires. But this problem has a twist. The current carrying wires in question are each part of a simple circuit consisting of a battery and a resistor. As you can see, we have two simple circuits consisting of a battery connected in series to a resistor. On the left-hand side, we have a 9-volt battery attached to a 2-ohm resistor. And on the right-hand side, we have a 9-volt battery attached to an unknown resistance R. The circuits have been arranged so that there are vertical parallel wires of length 10 centimeters each, and they're separated by 5 millimeters. The question we're asked to answer is what value of the unknown resistance R makes the force between the vertical parallel wires equal to 5.4 times 10 to the negative fifth newtons. So what force are we even talking about? Well, we need to remember that any current carrying wire is going to generate a magnetic field that other currents can interact with. So the left-hand wire is going to generate a magnetic field that the right-hand wire can interact with, and the right-hand wire is going to generate a magnetic field that the left-hand wire can interact with. And Newton's third law tells us that those two forces are going to be equal in magnitude but opposite in direction because these make up an interaction pair of a current with a field in this case. So the relationship for the force that a current carrying wire feels in a magnetic field is F equals ILB. So the magnetic force is equal to the current times the length of the wire in the field multiplied by the field strength. Well, we have a value for force given, and we have a length given. We don't have a current, and we don't have a magnetic field strength. So I can look at the other information that I'm given, and I notice that for that left-hand circuit, I have a voltage and I have a resistance. And then I can remember that, Ohm's law, voltage equals current times resistance. So I'll be able to find the current in the left-hand circuit. So that must be the one that I'm talking about that's going to be generating the magnetic field that the right-hand wire is going to be able to interact with to find that force. Well, how do we find the magnetic field due to a current carrying wire? That relationship is B, the magnetic field, equals mu naught, the permeability of free space, multiplied by the current divided by 2 pi r, where this little r is the distance between the current carrying wire and the point in question. So in this case, it's going to be the 5 millimeters because the wire that's feeling the field is 5 millimeters away from the wire that's generating the field. So now we've laid out the path through our problem. We know the relationship for the force that a current carrying wire feels in a magnetic field. We know that the left-hand circuit must be generating the magnetic field that the right-hand circuit is feeling. We can use Ohm's law to figure out how much current is flowing in the left-hand circuit to then be able to figure out what magnetic field is it creating at the location of the right-hand wire. So you ready? So we'll start with the information for our left side circuit, and we'll use Ohm's law, V equals IR, to solve for the current in that circuit. And we'll find really quickly, apparently I don't remember how to write my numbers, that the current in that left-hand circuit is 4.5 amperes. Okay, the next step we laid out for ourselves is that we're going to find the magnetic field created by the left-hand circuit's vertical wire. So using B equals mu naught I divided by 2 pi r, remember that mu naught has a value of 4 pi times 10 to the negative 7th. The current in the left-hand wire that's generating this magnetic field was 4.5 amperes. And then we'll divide that by 2 pi times the distance between these two wires, which was 5 millimeters, which is 5 times 10 to the negative 3rd meters. So the magnetic field strength at the location of the right-hand vertical wire is 1.8 times 10 to the negative 4th teslas. Halfway there. So now that we know the magnetic field generated by the left-hand wire, we can come back to that very first equation, F equals ILB, because we know the force that the wires are experiencing, and we can figure out how much current must be flowing in that right-hand circuit. So recall that the force we were given was 5.4 times 10 to the negative 5th newtons. And we're finding the amount of current that's going to feel this force in the right-hand circuit. Our length was given as 10 centimeters, which we need to make into meters. So 10 times 10 to the negative 2nd meters. And the magnetic field strength of 1.8 times 10 to the negative 4th teslas we just calculated. So our handy-dandy calculator will tell us that the current in that right-hand circuit must be 3 amperes. Last but not least, how do we now get the resistance R? Well, we've got a current, we've got a voltage, Ohm's law. And we end at last with a resistance of 3 ohms in that right-hand circuit. This is by far the most unique application of all of these ideas that I've seen in 22 years of doing physics. So I hope that you found this solution instructive and an interesting way to demonstrate how we can pull these physics ideas together. The most important takeaway here is that even I, an experienced student and teacher of physics, had to think my way through the problem. I started with the relationships that I knew and could figure out based on the given information, and then I had to figure out how to piece those things together to get to this final answer. Thank you so much for joining me today. I'm Brandy Heflin. You can find me online at brandyheflin.com and on Facebook, Physics Tutor Brandy. My page is Brandy Heflin Physics. I'd love to connect with you further to discuss your personalized physics instruction needs. I love physics and I love helping you. Until next time.